Hey, it's Horner, and this is Circular Motion. It goes round and round. For this part, we're going to talk about uniform circular motion, and we know that uniform circular motion just means that you have an object going in a circle at a constant speed, and that is the very most important part, is that it has a constant speed. But it does not have a constant velocity. The velocity is tangent to the circle. So you'll notice that the velocity is always changing because the direction is changing. We always have to remember that we have a radius r here, and that radius r will be the same the entire time too. Period is just the time it takes for the object to go around one time in a circle, and that would be one revolution. And the distance around the circle is the circumference, and the speed around a circle is 2 times pi times r, and we're going to divide that by t, where t is period. And I know it's tempting to say it's time, but we really want to call it period because that is the time for it to go around one time. For example 4.9, we have a rotating crankshaft. And so I have a 4 centimeter diameter crankshaft. It's turning at 2,400 revolutions per minute. And they want to know what is the speed of a point on the surface of the crankshaft. So that would be our tangential speed. So we can put Vt. And we first have to convert the 2,400 revolutions per minute. So this is a revolution per minute to revolutions per second. So we've done that. And then if the crankshaft turns 40 times in a second, the time for one revolution is just 1/40th of a second, but you really need to convert that into a decimal equivalent. And then the speed of a point on the surface is going to be 2 pi r, so that's all the way around. And we're going to divide that by t, and 2 centimeters is our radius. Be careful because this was diameter, so we have to divide it by 2. And then we have to convert it to meters, which is 0.02 meters. And we divide that then, once we multiply it times 2 pi by 0.025, and we get 5 meters per second. So that would be the speed in a straight line. So sometimes they call this linear speed. Other times they'll call it translational speed. This is angular speed, and angular speed can also be represented by the Greek letter omega, which I affectionately call butt, because it looks like you're sitting down from behind. And so this would be the angular speed or the angular velocity. On the angular position, we know that we're not going to use xy coordinates. Now we're going to talk about the position of a particle using this arc. And the arc here has our angle. If we go counterclockwise, if we go in this direction, we're going to say that our position is positive. So that would be positive theta. If we go this way, then it's going to be negative theta. And so theta is our angle, and it will be in radians when we do this. And you'll get used to that in calculus also. The arc length of a particle that travels along the radius of a circle. So if you remember, if we go back, you'll notice that we do have an arc length here, and that arc length is s. So that's how long the arc is at a particular angle formed by that particular radius. And that is just the angle in radians is just that length of that curve. So there's our curve again, divided by, and then if this was the center of the circle, this would be r. So it would be this thing divided by this thing. One revolution we know is 360 degrees. That is 2 pi radians. Those are the same, and so 1 radian is about 57.3 degrees, or about 60 degrees, so you can round it up. The displacement, so if I want to know how far it is along the curve, not from point to point, so you don't want to think about going from here to here, okay? That's displacement there. So the displacement along the curve, so is just this path length, is really the radius times the angle, but you have to make sure that angle is in radians. The velocity of a object, we're going to call that angular velocity. Remember we said that it looks like a butt. It is the Greek letter omega, and that is equal to the change in position in terms of radians divided by the change in time. So here's our change in position. Our change in time would be how long it takes to go from here to here, and if we divide that angle by the time, we're going to end up with our angular velocity. So that's just d theta over dt, or as the limit approaches 0, it's the change in the angle over the change in time. So big difference between change in angle, change in time, and d theta over dt, and it's because we're looking at that limit as it goes from, it's very, very, very close to 0. The SI unit for radians per second is radians per second, and remember, positive is counterclockwise. So positive is counterclockwise, clockwise will be negative. And that's kind of backwards from what you would think it would be, because when we think of a clock, when it goes in this direction is positive. But for what we're doing, that's negative. And if this thing spins this way, then that is positive. So that's the difference between the two. We're used to, if we have a position versus time graph, if we find the slope of that position versus time graph, we know that that is the velocity, and that's the slope. Same thing, but when we do circular motion, instead of x, we're going to use theta, t, and we get this, and then this will be our angular velocity. We are used to final position is equal to original position plus velocity times time, but now in circular motion we're just going to say that it's the final angle in radians is equal to the original angle plus the angular velocity or speed times time. And we'll talk about angular acceleration when we get into rotational motion a little bit more. So this is a good example of graphical representation of motion. We have the angular position of a wheel painted on a dot at the edge, at the very edge. And we want to describe the wheel's motion and draw the angular velocity versus t graph. So here we see that we are rotating and we are getting a larger and larger value. So it's got to be going counterclockwise here. Here it goes clockwise, and here there is no movement at all. And so it's just sitting at that point. So that's our figure. If we go on to the next one, we're going to actually find out what these are. So if I go from 6 pi radians and I do that in 3 seconds, then my angular velocity here is 2 pi radians per second. If I go from this point to this point, now I've got 4 pi minus 6 pi. That gives me 2 pi, negative 2 pi radians. And we do that in 2 seconds. So that's negative pi radians per second. And then here we're not moving at all. So that's just 0 radians per second. We've got all these. Now we need to create a omega versus t graph, and so we're at 2 pi radians. And then this, you can do a dotted line. You don't want to do a solid line. That means that you are traveling at that speed at that very second. You're traveling at all of these speeds at that very second. You can't do that. That's not possible. So then we dive down to the negative pi, and then suddenly we are at 0. The next thing we're going to take a look at is angular velocity and period and how they kind of go together. So this is really a frequency. So if you remember, frequency is equal to 1 over period. This is the same type of thing, but remember 1 for angular frequency is going to be 2 pi radians. And period is equal to 2 pi radians over the absolute value of the angular speed, or the angular velocity, or the angular frequency. This problem is called the roulette wheel. It is 4.11. I have a small steel roulette ball. It rolls counterclockwise, so we know that that's positive, around the inside of a 30 centimeter diameter roulette wheel, so we're going to put 0.3. The ball completes 2 revolutions in 1.2 seconds. What is the ball's angular velocity? So here we've got 2 pi radians divided by our 0.6 seconds, and that gives us an angular velocity of 10.47 radians per second. So notice that we did not need to have the 0.3 for this part of the problem. For the next part of the problem, they want to know what is the ball's position at 2 seconds. We're going to assume that our beginning angle is 0 radians, and since the ball starts at that, after 2 seconds, its position is going to be 20.94 radians. we need to now go around that 3 times. And so if we go around that 3 times, that'd be 3 times 2 pi radians plus 0.333 times 2 pi radians. And so in other words, at 2 seconds, the ball has completed 3 of our revolutions and is 2.09 radians or 100 degrees into its 4th revolution. So the observer would just say that the ball's position or its final angle is 120 degrees, which you could then also do in radians, kind of the same time. This is part 2, and this is velocity and uniform circular motion. So velocity vector of a particle moving in a circle only has a tangential component. So the velocity vector for a particle moving in a circle only has a tangential component. That is the rate at which that arc length is changing divided by the change in time, and remember S is arc length, and that is from the positive x-axis. So if I take the derivative of this, I end up with Vt is equal to ds over dt, so that would be r times the change in the angle times the change in time. And remember, d of the angle divided by dt is the angular velocity. So now we have gone through and made the derivation for tangential velocity. So if I know the angular velocity, I can multiply that times the radius of the path, and I end up with the tangential velocity, or how fast it's going in a straight line. So remember, this is what we call linear, and then this would be the circular component. So I can go thinking about a wheel on a car, and if I know it makes so many rotations, if I know that this thing makes so many rotations, and let's say that it makes two rotations, then I can convert that into radians, and then I can go and find out what that is in radians per second. If I just multiply that times r, I'm going to get the linear velocity, which is kind of the way to do it. Velocity in uniform circular motion, remember it's positive counterclockwise, negative for clockwise. A particle moving clockwise at 2 meters per second and a circle radius 40 centimeters has an angular velocity, because remember here it is moving clockwise, it's going to be negative. So that's negative 5 radians per second. So here we've got it clockwise, so we know that this linear or tangential velocity is negative, and r is going to be 0.4, that is our radius. Vt and omega are both negative because we know that motion is clockwise, and sorry, I think I said counterclockwise, it is clockwise. And if you notice, the meters cross off and we're left with something over a second, which is a hertz. And so radians is really a dimensionless unit. So we really don't even need that. If we take a look at the acceleration and uniform circular motion, now we're going to look at how we have this acceleration that points in the center. So remember, that is the centripetal acceleration, so that's AC. And if you remember, AC is equal to v squared over r, where this is tangential speed. And so that's the centripetal acceleration. If we go through and think about dv, so that is the change in the velocity. So if I have a velocity number 1 and then it moves a little bit and I have another velocity, it's a final velocity, and I find that change in velocity, that is really the centripetal acceleration. So if I want to find the magnitude, I can make that isosceles triangle, and then I can solve for that by just taking the velocity times the change in the angle. Going on, if I have dv, which is v d theta, then for uniform circular motion at a constant speed, which is the change in position over the change in time, I'm going to take r, which is the radius, times the change in the angle divided by the change in time. And if it rotates through this angle, here's my equation. And if I combine the two equations, I get what we were talking about earlier, and that is the acceleration in the terms of the centripetal acceleration is equal to v squared over r. So that's toward the center of the circle. The centripetal acceleration is also then equal to omega squared times r. Because remember, omega, so acceleration here is equal to, well, let's go back. Velocity is equal to omega r. So if I square this, I'm squaring both omega, so that's omega squared times r squared. And acceleration would be then, centripetal acceleration would be this squared times this squared, so that's my v squared. And then I want to divide that by r. And when I divide it by r, it gets rid of the r on the bottom and one of the r's on the top. And that's why this equation comes out, and it is the same as this. So no difference at all in those two accelerations, just found a different way. If I have a Carnival Ferris wheel, it has a radius of 9 meters and it rotates 4 times per minute, they want to know what is the magnitude of the acceleration that the riders experience. So here we know that velocity is equal to 3.77 meters per second. Once I find that linear velocity, I can square it, divide by the radius, and they see that they're feeling about a 1.6 meter per second acceleration. Let's take a look at non-uniform circular motion and angular acceleration. So now we're starting at a velocity equal to 0, so that's our original velocity, and our final velocity then is going to be equal to some number that's going to be greater than or less than 0. So if we go through and we take a look at 2 points on the wheel and turn it through the same angle, we're going to notice that we have two angular velocities that are the same. So for example, if I have this point right here, number 1, and I have this point, number 2, if they go around one time in a circle, they've both been around one time. Okay, one doesn't go one time and one goes 2 times. They both go through and displace the same amount. So our angular velocity is the same. However, the one on the outside is going to have a higher tangential velocity. So that's the difference between the two. The angular acceleration, alpha, is equal to the change in the angular velocity divided by the change in time. So I usually say if you will go fishing, you sit on your butt for a very long period of time. So that's just alpha is equal to omega divided by t. And our radians per second squared unit just comes from the fact that this is radians per second and this is a second, so radians per second squared. So that is non-uniform circular motion and angular acceleration. Alpha is positive if omega is increasing counterclockwise. So if I'm accelerating while I'm traveling in the same direction, then I will have a positive A, okay, a positive acceleration. If I am slowing down, okay, then my acceleration is negative. Okay, so here acceleration is positive because my speed is going in the same direction. So I'm speeding up counterclockwise. So this is positive and this is positive. If I am slowing down counterclockwise, which means that my acceleration is now less, okay, my acceleration is going in this direction. So sometimes I like to do this. I know that my velocity, my angular velocity is going in that direction, and my acceleration is going in that direction. Here, my acceleration is going in the opposite direction. Notice how it is going in a clockwise direction. So it's negative because it is clockwise. Counterclockwise is still my initial angular velocity. If my initial angular velocity is negative and my angular acceleration is positive, then I'm slowing down again because they're opposites. So remember, if they are the same, you are speeding up. If these two are different, then you're slowing down. Here they're different, we're slowing down. And finally here, oops, I don't want positive, I actually want negative. I have negative and negative. I'm speeding up clockwise. They're both negative and I'm speeding up. So that's really important that you understand these. So if you're having trouble, sign up for Core Time and I can help you with the difference between the two. This is the rotating wheel. This is a graph of angular velocity versus time. And so you'll notice that we have 3 sections here. Here we don't have any acceleration at all, so acceleration here is equal to 0. Here we have positive acceleration, and here we have negative acceleration. So we're slowing down here, and here we are speeding up. So we're describing the motion of a graph of angular acceleration versus time. So the wheel starts from rest, it speeds up counterclockwise. So be careful, because even though that graph looked like this, and we had omega here, and we have time here, because this is a positive slope, it's got to be going counterclockwise. Then it's not accelerating at all, it's still going counterclockwise, and here it's still going counterclockwise. The problem is our acceleration here is we've got a positive acceleration, we have zero acceleration, and here we have a negative acceleration. So that's why you see this. So be very, very, very careful when you think about these as they go through. Just pay attention to the slope. Slope here is negative. It's got to be a negative acceleration since it's a velocity versus time graph. Rotational versus linear kinematics, they're basically the same. You just have to remember that this thing, if it's going in the counterclockwise, it's positive, clockwise is negative. Same thing for acceleration. Here, velocity and acceleration in a straight line, you can define, oh, maybe going to the right is positive and going to the left is negative. You could also do it the opposite way. Here, you don't have that, so you have to be very careful what you do. If we go back to the roulette wheel, we have a small roulette wheel. It has a 30 centimeter diameter, spun at 150 RPM, but it slows to 60 over 5 seconds. So they want to know how many revolutions does it make. So we're going to use our kinematics equation. This one is the change in position is equal to the original velocity times time plus 1/2 of the acceleration times the change in time squared. We have our original velocity, we have our final velocity. Okay, so we've solved for both of those. And then we want to find the acceleration, so we just find the change divided by the time, and that gives us, there it is, a negative acceleration. And so we plug the numbers back into our equation, and we end up with 54.9 radians. Because 54.9 divided by 2 pi is about 8.75. The ball completes 8.75 or 8 3/4 revolutions as it slows down to that 60 RPM. Tangential acceleration, this is different. So now remember, acceleration in going towards the center is called radial now, because we're adding some more things to it. You can still make it centripetal if you want to. But we really want to switch it when we look at tangential acceleration. Tangential acceleration points tangent to the circle. Centripetal acceleration or radial acceleration is towards the center. And then if you add those two vectors together, you're going to get the average acceleration. And that's for non-uniform circular motion. So this does not point towards the center. So now we have something that is either spinning up or spinning down, speeding up or slowing down. And so our overall acceleration is not towards the center like it would be if it was traveling at a constant acceleration. It's either speeding up or slowing down. So that's in non-uniform circular motion. The magnitude of the acceleration, we just do the Pythagorean theorem. If AT is constant, so if this AT isn't changing, we can use these equations, that a tangential velocity is equal to omega r, and we can see that alpha r is our tangential acceleration. So same thing that we did before with velocity or with position. Remember we said that the linear position is equal to the angle times the radius. We can do the same thing here with the tangential acceleration. So this is acceleration in non-uniform circular motion. So it's speeding up or slowing down. I think earlier I said the acceleration is changing. It's not. It is constant, but our velocity is changing. So it is speeding up. So this guy stays the same length. The Vt is equal to omega r and At is equal to alpha r. They're analogous for tangential velocity and acceleration. So if we go back to 4.14, that example, we know that the acceleration was 1.89 radians per second squared. And so if I want to know what the tangential acceleration is, I just multiply the radial acceleration times the radius, and I get the linear acceleration. And that, I think, is the end of that one. If I want to analyze rotational data, For example, I've got something that's turning. These are some times, and these are the angles at those times. I've attached a shaft encoder. I've got a 3 centimeter diameter axle, and I'm trying to measure the startup characteristics of this very large industrial motor. When it reaches a full speed, I know the angular acceleration is 0, but it should be constant during the first couple of seconds as that thing speeds up. So that's what I've done. If I go on, I have to see if the data will support my hypothesis, and then find out what is that angular acceleration. Okay, so I've got a blade here. Maybe it's an airplane blade. It's an industrial motor for an airplane, and I want to see kind of what's going on in terms of, here's my tangential acceleration, my radial acceleration. I know my angle here, how far it's traveled, and I know its a velocity as it's going through. So when that motor starts to spin up, my initial conditions are 0. The angle time equation for rotational kinematics is the same as it is for linear translational. And so I can use y is equal to mx plus b, where y is my angle and x is going to be t squared. So a graph of the angle versus t squared should be a straight line if this is traveling at a constant velocity. So remember, we said that if this is y, here's my slope. Oop, there we go again, 1/2 of the acceleration, and then this is x squared. And that should be a linear relationship between the two. So if I want to know what is the angular acceleration, I can just take 2 times the slope, which is going to be that guy right there. So here we go, done that. We end up with this equation. When I plot the t squared and the angle, I get this guy. So I know that this is 1/2 of the acceleration. So I really need to multiply that guy times 2. When I do that, I'll end up with the right acceleration. So you'll notice that this number has become 549.2. If I multiply that times pi radians divided by 180, I'm going to get about 9.6 radians per second squared. And that would be the answer in radians per second squared from acceleration. If I want to know the magnitude of the linear acceleration, I have to first find the linear acceleration of that blade tip. Once I do that, the centripetal acceleration increases the rotation speed as the rotational speed increases. So now I can find out if I have this acceleration minus the tangential. So this is my total acceleration. If I do that, I'm going to get 9.31 meters per second squared for the radial, or the centripetal acceleration. My corresponding angular velocity is 4.95 radians per second squared from the equation that we have here. And so now we can see that it takes about 0.52 seconds for it to speed up like that. And that is the end.